basic fact about the binomial. Then we apply that one again. Now I change the assumption. Okay, I change the assumption from number 5 to be number 20. You want to try 20 trial. Okay, like this. And we want to compute the mean and the standard deviation of the number of winning bottle mom dumb. This is the third question. So not the same like the second question. Okay. Then also you want to compute the probability that you get 2 or 3 lucky tickets. So there are two different questions here. We can say the first one here is the question A, and the second one here, the question B. You have two different targets. So we define the capital X to be the number of lucky tickets among total 20 bottles. You see? So if you define the number of lucky, that means the number of successful events. Therefore, by the theory, you can say, well, the capital X can be described by the binomial with the parameter here. By the way, in the general case, for the binomial models, in my textbook, I write just like this one. I don't write the full name binom, okay? But the meaning are the same. In my textbook, I write in the general case the binomial with n trial and small b here, the successful likelihood. Okay, so in this case, we apply n here. You get 20 and you get small b, like this one. And you know the mean or the expectation. The formula in the last slide tell you this one. Okay, so in average, the average number of lucky tickets will be only 1.2 tickets. But the standard deviation also by the one we know before, square root of the product here, you see? And that means the second one by our theory will be sigma, and the first one we call mu, remember? The expectation we call the mu. Now we just finished the question A. You see, I computed for you the mean and the standard deviation. You see, so we finished question A. For question B, again by the same argument. Some people say that he got the value. Tân Lộc said, look to the chat box. The other student, please calculate the standard deviation again to confirm his answer, please. Lộc said that sigma actually will be only 1.062. So we have to double check it right now. His answer. Confirm me, the other student. Is that true or my value is true? Which one is more precise? You get 1 minute to compute that and tell me your confirm. Okay. 1.96 or 1. Good. So Hồng Quân 2. Okay. So I just update that I believe you. Okay, so this one you should update to be the new value from your friend. So they got about this one. Okay, that's fine. Quang Huy, Hồng Na, Hồng Quân, and Tấn Lộc, three guys got the same value, so we follow that one. Okay, so forget this one is wrong. Now compute the probability here. Teacher, the micro of. All right, why up again? Now, can you hear me again?
Yes.
Good. So we continue from here, computing this probability of the union to event, and they are disjoint. You see, so by the HCMUT of Kolmogorov, you apply this one, the formula here, and n to be 20. Oh, okay, the slide. Sorry. Okay. So anytime we resume, then we have to restart things. Now, can you see the slide?
Okay.
Good. Okay. The first livelihood will be here. You see the formula right here, and choose number two, then and choose number three. You know the last formula I asked you. Now we apply here. Then this is p up to x, and this is 1 minus p up to uh, small n minus x, you see. So that means 17 for the second case, and this one for the first case. Anyway, you can answer question B easily from here. Okay. So the more problem is about the modeling, not about the formula. Okay. So we are entering the last session, which is the most interesting one, where after you learn everything, okay, the theory, now you want to apply the theory of lecture number 7 here to practice your skill. We call the problem solving skill. Okay. So I assume that you study and you understand detail any formula we working in the last 2 weeks. Okay. Now today we spend the last hour to practice many exercise which I classify into 4 groups, A, B, C, and D. Aha! Remember, in the final examination, the question will come from here. From here. Okay? From lecture number 7. Okay, so for groups, the first one we practice the experiment and sample space. The second group we learn the technique for computing the probability of some event. Then we practice the bias theorem and independent event. Finally, we see how we apply the probability models. I mean the Bernoulli, the geometric, and also the binomial as well. So I don't solve everything for you. I just provide some hint if necessary. So in the group A, you start from beginning, from elementary concept, experiment and sample space. We consider experiment, so this is, you can say, the first problem of group A. We can say that, okay. We consider experiment in information transmission in banking sector. Your experiment to be select a sequence of 5 letters for the transmission of a code in a money transfer operation. Okay, and because you define your sequence of code will consist 5 letters, so that means we can model the code by this one. The code will be the sequence of A1 up to A5. Okay, so they are all letters to be chosen. So the first question here will be, so this is problem 1. I say problem 1 in group A. And the first question here, you want to determine the sample space. So this is the first question here in problem 1. And you have to remember the concept sample space when you do some experiment. We call the random experiment, right? So one outcome will be a code. A code means a sequence of 5 letters. Therefore, the sample space will be the setup on possible sequence from the 5 letters. So this one is a code. And because you say the ordering is important, so you have to write with the bracket outside here to mention that the ordering is important. So you look to the chat box. I say in a code, like your password, the ordering of letter is important. Okay, like your name, for instance, you can see example in your name. If you move around your character in your name, then you get different name, right? Okay, so for instance, I take Nam. His name is Nam. And you see, if we move something like this, then you get different name. Nam become Mong, you see. The second one here, the ordering of the letter in any sequence is important. So the second example is like that. Hua is meaningful, but the second one is not meaningful, you see. So therefore, you have to consider the ordering here inside the brackets, where the AI can be selected from the total number of English character from ABC up to Z. And you ask yourself, well, after you describe the sample space, and you need to know how many elements how many elements of the symbol space. That means you ask yourself the cardinality of the symbol space. Understand? The cardinality we denote by this one. The symbol space we know, of course. We know how many elements inside that symbol space. And you have to employ combinatorics again. You see? And the problem we multiply the in that sequence product at the time you build up one single. So that means multiplication rule I also call product rule, and by combinatorics, by that rule you say that the first position, how many character in English? 26. You see, this is for the first position in the code. The second position will be the same because you allow A2. So that's why you understand. That's good. So I am try explaining the meaning of the outcome. I don't ask you the outcome, right? So we want to understand the theory. Why do we get the outcome? Hmm? Yeah, correct, of course. We call the multiplication rule or the product rule. One vector like this, we call a code, or we can say a symbol point, okay, or a symbol unit, or a symbol element, okay. So this is my question. The next question in problem 1, you should do yourself. You want to determine the event that all the 5 letters in the code are the same, and then you describe that one and you have to compute the probability. You do not see the slide? Wow. So communication is not unwavering. Huh? So you do that yourself, huh? I don't. I don't check this one. You have to do yourself and check with your friend, okay? because we define the quiz mean that means easy exercise. So let's say that Khoa Phạm Nguyễn Nam Khoa, he said that the event he will have 26 value. So you don't say that, you have to say like this Na Khoa. You have like this one. He does the number, right? And if you want to say about the event, then you have to write explicitly the event. Understand what I'm saying? So thing like that. I mean the number and the set are different idea. Okay? Okay, so we move to the group B, where you want to compute the probability of some event, and I recall you the complement rule, the union rule in the case A and B are disjoint. So you want to do something in generic case like this one. Okay? So how can we compute the probability of event A for any event inside the sample space? So you have to combine things together. Not only the product rule, not only the permutation rule or the combination, but you have to combine all of them. The right way, the right tool for the right job. So this is the policy when you solve. So let's see how can we move on with that. I recall the multiplication rule. So in your textbook, you also call the multiplication rule by the name product rule. Okay, product. Multiplication means the product of the event. Okay. So you have some operation consisting of case step, and you want to compute the total number of cases. Then you have to compute in step 1 how many, in step 2 how many possibility, and up to step K. Then the final answer will be like that. Okay. So group B, we say this one is the first problem in group B. So we can call this one B1, first problem. We talk about website design, and you can do that yourself by applying the product rule here. So we move fast here, okay, because they are more important one. About the permutation rule, so we have to remember originally what is the concept permutation. So we define a permutation will be a unique sequence of distinct items. So we can count. So this is definition, and this is the way we compute the number of permutation. Okay, the first one is a concept, the concept of permutation. And after you understand the concept, then we move on with the second one here. How many times, how many cases we can build up permutation. Then that means the second one, we talk about a number of permutation. Okay, number. So the concept are different from number, right? Concept, permutation, and this is the total number of cases you can build. Okay. If you have two characters, A1, A2, let's say, and A1, A2 can take from 26 English character. You see? But now we don't talk about the total, we talk about the permutation. So we have to consider only you give me A1, A2. So we don't talking about that. You are given two characters. So this one definitely not the same like A2, A1, you see. So the left hand side is one permutation, the right hand side is another permutation. That means the total number of permutation given character A1, A2 will be exactly two permutations. Okay. So this example for the case where you have small n to be number 3. So the example up there mean n to be number 2. So they are different example. Okay. So if you have n to be number 3 character, that means you are given 3 small letter A, B, C like that. See what I mean? Then you can build up the first permutation like here. Then you can move the position of C and B, and you get the second permutation, you see. So in total we get this. The total number of cases will be 3 factorial in the second case. We see number 6 you get there, right? You need to remember the concept factorial. Now we consider the next concept we call the subset permutation. So we don't have moving the position of n item. You are allowed to change position only to k character, where you allow number k here go inside this range. You see, obviously the case where you get k equal to n, that means you have p and n. You see that what I mean? Then this one will go back to n factorial, the original number of permutation. But otherwise, if case actually have the rubber meaning, that means when small k here actually smaller, probably smaller, then this one and that one are different. See? So, briefly speaking, the last formula here is a kind of generalization from the one we learned up there. Okay? So, this is about the permutation. We employ that one when you compute probability of event. So, this is second techniques when you compute likelihood of event, you require that one. Okay, so we can the score, you know, very simple the location. You can put your memory put the file to a plugin. The 8 component can be see get the position for so like need to be can you do you hear me? Guys, do you hear me? Hello there. We are moving to the third counting technique. Lost connection again. Hear me again, guys. Nguyễn Quang, do you hear me well again? Trần Ngọc Oanh, do you hear me? One. Okay. So you see the slide there, Vic Hòa. Can you read the slide, the first row of the current slide? Hòa, Nguyễn Vic Hòa.
Yes, yes.
Read that line,
Uh,
read that row. Read that.
counting technique, counting technique three.
Okay, thank you. That's fine. Good. So we can move on. So technique number two. Thank you, Hòa. Turn up your audio, please. Hòa. Turn up your audio. Hòa. Okay. So technique number two is about permutation rule, and technique number three we talk about combination. Okay, the last one permutation, the current one combination. So we talk about the way we choose k item from n item. So selection of k item here, we don't count the ordering. Okay, when we talk about permutation, you have to take care the ordering. Okay, the order of the position is important. But when you talk about combination, then we don't care about the ordering. So we just take a subset of k element inside and tie some set with n character. Okay. So the subset here having k element we get from the entire bigger set n element. So if I choose, for instance, us here to be having 3 elements, then I choose k to be number 3, then you see there only one combination like this one. So you can say the left hand side we did not like a k. Okay, so that means if k equal to n, then you have the subset will be entire the whole bigger set outside. But if you choose here k to be number 2, wow, so that means this one now become really smaller than the total number of items here, then you actually can list out there are 3 subsets. Okay, you understand me? So the AK here in general case, so the first subset here you have U not here A, this one also the second one, this is the third one, they are all subset of your original set here. So by default you understand that if you allow the permutation, then the number of permutation will be always bigger than the number of combination, because the concept permutation take care of the ordering, and the combination does not take care of that. So if you want to compute the number of combination, the number of combination, then last time some people answer me, we see the right hand side here, the number of combination, and we did not this by notation here, also by this notation, and by default by argument here we just compute by taking this k permutation, the number divided by k factorial, because we don't care about ordering in combination. So that's why you see this one here. Okay, so formula number 6 also useful in probability. Then you can move on with that. We practice the 3 techniques so far. Now we go back to our coding example. You randomly transmit a sequence of binary signal. So the binary signal can be something like this. Okay, if you say there are 4 characters, but because randomly, then you may also see something like that as well. You just change the position here, you see. So we want to ask something particular, right? This one, what is the probability that 3 over of 6? So that means you understand that you want to build up a code with 6 position. You see? So in this example, we are talking about the value n to be number 6. You see what I mean, right? Then you want to compute the probability that 3 characters from the total 6 are becoming number 1. So that means this one is okay, the first one, because you see 1, 2, 3 characters are number 1. But the second one here you count and you see only two number 1. So the second one is not good. Okay. Then you have to symbolize that event by this one. This is my notation for that event. Denote the event to observe 3 over 6 signal to be number 1. Then you have to compute the total sample space, right? So the first row here tell you the sample space, because actually you want to compute by elementary theory. The probability actually is the ratio of the cardinality of a tree divided by the cardinality of the sample space. You understand? Okay. So therefore, you want to know how many elements are there in the sample space, and because you allow 6 positions, okay, and by the product rule, 1 position allowed 2 value, and you have 6, and by the permutation rule, then you get the total number. The total number of elements inside the sample space will be exactly this one. Okay. So this one will be this one, 2 power 6, the permutation rule. But then how can we compute the numerator up there? Okay, you have to do some argument. You say that the point must be equally probable happening in that one, and 1 point inside the sample space will be a combination of 3 symbol you put into the 6 empty position. You go like this one you see here, the first example here. I have total 6 position and you have to put 3 number 1 inside, you see. So 3 signal mean 3 number 1 you put into the 6th position in the binary sequence. You see that what I am saying? Then that means one pawn now become a combination of 3 elements from 6 elements. You see? Therefore, the total number of combination of k item, you see, chosen from 6 items in this case, will be this binomial coefficient. So you know the numerator here, which is this number. You see? Then, therefore, the final one is just like that. That's okay, right, people? Trần Ngọc One, do you understand my argument? Please answer via audio. 1. Yes. 1 say yes. Okay, here, well, that's good. So, to solve the example like this one, you see, you have to combine the permutation rule and also the combination rule together. And don't forget the definition of probability here, the ratio of this and the ratio over this one, okay? So, when you solve exercise, you have to combine many bits of information. Now you move to the third group. I define to be group C. We move to independent event and then also the Bayes theorem. Okay. Independent, that means the occurrence of one event are not affected by other event. So you have in total, let's say in this case, we can say the first problem of group C, I call problem C1. You have 5 identical departments are designed in a commercial bank, and we define E1 up to E5 to be the event that the 5 departments comply with the quality specification. Okay. Quality specification means no defective case happen in that department, no error happening in the department, and we assume that they are independent. That means if some certain bad event happening in the first, the bad event does not impact on the second department. Okay, we define the concept independent before, then we talk about the mutual independent in that sense. That means any happening from EI does not impact on EJ, where I and J, if you use the index, I and J are different departments in the bank, and the value of I and J can go from number 1 up to number 5, you see. So very clearly, right? Then you want to compute that the probability that all the 5 departments are really, get the good quality. I mean, they do not consist of any defective. Okay, good. That means no defect. So that means the first one is good, measured by this number. The second department also good, measured by this, and the last, the E5 also good. And because they are independent, then the left-hand side here can be computed via the right-hand side, which is the product of this one. Okay? So my question is, can people remind me what is the name? How do we call the name of the left-hand side? You can write the answer in the chat box. What is the name or the meaning of the left hand side? Write in words, or you can say in sentence. Turn on your audio to say, or you write the answer in the chat box. Left hand side of this equation, tell me. I would like to hear the name of the left hand side. Vin said probability of independent event. This is good answer but not perfect one. Nguyễn Hữu Đức, Phạm Hữu Đức say independent probability not why perfect, good but not enough. Anything else? Anyone else? The left hand side of this equation. Independent probability not perfect, correct but not perfect. I would like to know the complete meaning of the left hand side. So Vinh, Đức and Khoa, try your best. Thank you. So that's good, but not enough. I would like to know the real name of the left hand side. Of course, they are the probability of 5 independent events. Of course, we are talking about that. But left hand side have a real name, very beautiful name. You have to get used to that name. Independent probability of EI with I from 1 to 5. That's also correct, but not fully. Vin said again, bear Y is independent. No. So you have one more. Lê Hoàng, discrete probability, not perfect. Try your perfect. Try your more thinking, okay? More critical answer. So you have one more minute. Don't worry, just thinking and tell me. The name of the left hand side. The formal name of the left hand side. Product of independent probability. Yeah, this is the black, not the black, sorry. This is the, how do I say, the down to earth definition, but it have a good name, better name for that. So I will answer, I will write here, okay? This is the, technical name of the left hand side. Okay, now we can move on. And because they are independent, therefore that joint probability must be calculated like this one, okay? And because we assume that the department come from the same production process, that means the same company, then by we consider the 5 departments are homogeneous, then we can assume that the probability of the EI are the same. That means we think that P of E1, all of them are the same. And because they are the same to be a constant, then you can put one value parameter P for all, okay? and employ the final argument, then you get the answer here to be p power 5. But if they are not homogeneous, if not, then you have to use different parameter for different department. You see what I mean? If they are not homogeneous, then you have to write different parameter for different department. In this case, we assume, okay. So this is the real question for this problem. After you understand everything now, then this is the question, okay. We want to compute the probability that one department is defective and the other one 4 are non-defective. So this one is not good. You want to compute for one only, where the other 4 are good. We want to know that probability. Okay? How can we carry out that task? And this is the answer. You have to define new event like this one. A1 to be the event that one of the 5 are bad, defective. And you have to compute that event. Okay? And you know that we don't know particularly which department is not good. So we assume this one is not good, the first department. Then the one here means the other 4 are good. But we don't specify clearly which one is bad, which one is defective. Then possible case will be like this one. Possibly that the second department also defective. Okay, so that means E2C, that means the complement of E2. E2, we define that the second department is good. Their complement of E2 means the second department is bad, okay, defective. And because the roll up on 5 departments are the same, what happened to E1 happened to E2 possibly, and what happened to E2 also possibly happened to E3. You see, then therefore you have to take the union, and then move on with E4 and E5. Therefore, computing the entire event A1 will be long like this one. So you have to imagine that the first one here is one event. We can denote by some name like this. Okay? And the second event like this one, K2, if you want to write capital K, and you see that the event here will become the union of 5 disjoint events. Disjoint means if we define K in that way, then you say that Ki disjoint means Ki intersect with Kj become empty set. Understand me? So what's a K5? K5 is the last one here in my notation. Okay, this is K4. Understand? And this is K3. And because the A1 will be the union of K1 up to K5, therefore by the HCMUT A3, yes, HCMUT again, common law very important. Give you the last formula. Give you the last equation, because you are computing the probability of disjoint event. Okay. Understand me? So that's why we have this one. So this is K1 and plus here, more, and finally this one. Then you have to explain. Upload from session problem to the rest on to this one is not about the problem. The problem 805 I put there already. This is the guideline for solving the problem. Okay, this is the guideline. You have to solve almost every exercise in the tutorial I put there. So this one is not theory. This one is the guideline for problem solving. Okay. So that's why I put a few questions here. I ask you to explain things, etc. So this is a review actually. So finally, we have about few more minutes, and this is the final group. We talk about using the probability model introduction, and the key problem here. How can we choose proper probability model to employ, where the model can be Bernoulli, can be binomial, or geometric. So the last section is right here. We have to apply the probability models. Okay, and the key problem here is how to choose. You have to read the assumption, and then you have to determine the sample space. You have to follow the group A. Remember, group A about experiment and sample space. You define the sample space. Then after you define the random variable, you have to determine the range. After you determine the range, then you have to say clearly which models. So in this example, you have to say, okay, geometric is the right one to choose. Okay, the problem here I raised here. You have to read carefully the assumption. The problem in semiconductor manufacturing. The concept we call the wafer contamination in personal computer. When you produce component for electronic industry, okay, you define capital X to be the number of wafer like the main board of computer. We need to analyze to detect particle of contamination. Okay, and assume that one wafer like one main board of computer, the probability to consist a defective particle will be 1%. Okay, and you want to determine the model for that probability model. Okay, so that will help you to realize the importance of probability models. All right. So the theory stops when you study up to down to binomial models, and the last one here just provide a hint for you to apply everything you learn in practical. So in this case, to apply the geometric, because we find the way like this. So here on Y to be a wave axis in that one. Then we did not small them to be a waveform in which the particle is not appear. So that means in practice when you be using Y here, that means this one you get contaminated, and if not, then the first one is okay, the second one is bad. Otherwise, the first two here are okay, the third one you get not good, you see, and then 1, 2, 3 are okay, and the 4 not good, so something like that. So determine this one is most important. Okay, then you count the number of value. Obviously, the number of value here the value of x becomes second, then you buy like the lucky when you buy Coca-Cola. So we apply the idea, but in the